On January 5, 1943, the cruiser Helena was operating in the South Pacific. A Japanese aircraft entered the reach of her 5-inch guns. The ship fired, and an anti-aircraft shell burst near the aircraft without striking it directly. That was precisely what the shell had been designed to do. Inside its nose was a complete radio transmitter and receiver. It also carried a power supply, safety mechanism, amplifier, and detonator. Together, those components had survived an acceleration violent enough to destroy ordinary electronics. Now they were rushing through the sky inside a spinning projectile. The radio signal reflected from the approaching aircraft. As the reflection strengthened, the fuse recognized the closing distance. It triggered the explosive charge close enough for fragments to cross the remaining gap. The projectile did not have to hit the aircraft. It had to recognize the correct instant. The aircraft went down. According to the United States Navy's wartime record, this was the first Japanese plane destroyed by a proximity-fused projectile. The engagement looked like another successful burst of naval gunfire. In reality, it marked the combat arrival of a new relationship between electronics, artillery, and industrial production. The remarkable part was not the original idea. Several countries had explored ways to make a projectile react to a nearby target. The remarkable part was making the idea small, rugged, safe, and reproducible. Each fuse had to become a miniature radio station built for its own destruction. It had to remain dormant while sailors handled the shell. It had to awaken only after leaving the gun. It had to distinguish a meaningful reflection from the violent electrical noise surrounding it. Then it had to function during a flight lasting only seconds. Failure at any stage could waste the projectile or endanger the ship firing it. Premature detonation near the muzzle could kill the gun crew. Delayed detonation would merely scatter fragments behind the target. An unreliable fuse would be worse than an ordinary mechanical one because commanders could not trust it. This was why the problem had resisted inventors for years. Aircraft had become faster, tougher, and increasingly difficult to predict. Naval fire control systems could estimate where an aircraft would be when a shell arrived. But estimation was not impact. A contact fuse demanded, a direct hit against a small, rapidly moving target. A mechanical time fuse required someone to predict the correct bursting time before the shell left the gun. Even a tiny error in range, speed, course, or timing could place the explosion harmlessly ahead or behind. Radar improved the estimate. It did not remove the final error. The proximity fuse attacked that last uncertainty inside the projectile itself. The fire control system only had to bring the shell sufficiently close. The fuse handled the final fraction of the engagement. This division of labor was the real mechanism. Radar detected and tracked the aircraft. A director calculated the firing solution. The gun placed projectiles along the predicted path. Then each fuse independently reacted when a target entered its effective neighborhood. A near miss was no longer necessarily a failure, but the shell fired by Helena represented far more than clever circuitry. Behind it stood British research shared across the Atlantic. American laboratories, naval ordnance specialists, glassmakers, battery designers, and mass production lines. Their task had seemed almost unreasonable in 1940. They had to place fragile vacuum tubes inside a shell and fire them from a naval gun. The electronics would experience forces measured in tens of thousands of times gravity. The components could flex, fracture, short circuit, or tear free from their mountings. Simply proving that a radio signal could trigger a fuse was therefore insufficient. The entire device had to survive the gun first. That requirement transformed a scientific concept into a systems problem. It also explains why Helena's engagement matters. The decisive object was not merely a radio hidden inside a shell. It was a disposable radio that thousands of factories and workers could build consistently enough for sailors to trust in combat. To understand how that became possible, the story must return to 1940. Britain was already fighting for survival. Aircraft were outrunning older defenses, and engineers faced a question bordering on the absurd. How could delicate electronics survive being fired from a cannon? In the summer of 1940, proximity detonation was not a single invention waiting to be assembled. It was a field of competing possibilities. Researchers considered acoustic, optical, electrostatic, infrared, and radio methods. Each could detect something under favorable conditions. War rarely supplied favorable conditions. An acoustic fuse might listen for an aircraft engine. Unfortunately, a shell generated tremendous noise during its own flight. An optical device could react to changes in light, but clouds, darkness, and sunlight complicated its judgment. Electrostatic methods also presented problems of range, consistency, and practical construction. Radio appeared promising because it did not require daylight or physical contact. Yet it demanded electronics small enough to fit inside a projectile. Britain had already investigated proximity devices for bombs and rockets. British information helped accelerate American work through the wartime scientific exchange between the two countries. British researchers also understood the far more punishing problem of gun-launched projectiles. The difficulty was considered so severe that a practical artillery shell fuse seemed unlikely during the war. A bomb drop from an aircraft experienced comparatively gentle release. A rocket accelerated over a longer interval. A shell went from rest to extreme velocity inside the length of a gun barrel. The United States Navy nevertheless made that shell its priority. Its principal dual-purpose weapon was the 5-inch 38 caliber gun. The weapon could engage ships, shore targets, and aircraft. Against aircraft, however, its effectiveness still depended on placing an explosion at the correct point in three-dimensional space. The Navy asked the newly created National Defense Research Committee to pursue the problem. A group led by physicist Merle Tuve became section. Its early work began at the Carnegie Institution's Department of Terrestrial Magnetism in Washington. The letter stood for Tuve. But the organization soon grew far beyond one physicist. Scientists studied signal behavior. Engineers redesigned components. Manufacturers learned to reproduce devices that laboratory workers were still changing. Naval officers translated operational requirements into physical limits. The project initially kept several detection methods alive. By the spring of 1941, radio had emerged as the strongest candidate for a gun-fired projectile. Section T then concentrated its effort on that approach. Its proposed circuit used the fuse itself as a tiny radio oscillator. The circuit transmitted a signal while the shell moved through the air. When the signal struck a nearby object, some energy returned. That reflection affected the oscillator. The changing response could be amplified until it triggered the firing circuit. This was not radar in the familiar sense of a screen showing range and direction. There was no operator watching a trace. The device did not identify the aircraft or calculate a conventional firing solution. It responded automatically to the changing radio relationship between shell and target. That simplicity concealed a difficult sequence. The fuse needed power only after firing. It needed time to travel beyond the danger zone around the gun. Its transmitter had to operate during violent rotation and rapid changes in position. Its receiver had to react at a useful distance without becoming dangerously sensitive. Finally, the detonator had to fire while the shell was still approaching the target. A burst after the closest point would throw much of its fragment pattern into empty sky. Every electrical component, therefore, became a mechanical problem. Glass vacuum tubes were an obvious weakness. Their internal elements could bend or break under acceleration. Connections that worked on a laboratory bench could separate inside a gun barrel. Batteries could leak, fail, or deteriorate while ammunition waited in storage. Even insulating material could behave differently in cold seas and tropical heat. The team could not protect the electronics by making everything massive. Every additional layer competed for extremely limited space. The fuse still had to fit the projectile and leave room for a useful explosive charge. The solution emerged through repeated redesign rather than one dramatic breakthrough. Vacuum tube elements became smaller and more firmly supported. Assemblies were mounted to distribute stress. Components were packed into protective material. Connections were tested against shock. Spin, temperature, vibration, and storage. The entire package was treated as expendable ordnance, not as a delicate radio set. Testing produced failures faster than successes. That was useful. A transmitter disappearing during flight revealed that some component had broken under launch stress. A signal continuing through the expected flight showed that the circuit had survived. In January 1942, experimental fuses were fired vertically from 5-inch guns at a secret facility in southern Maryland. The immediate objective was not to destroy an aircraft. It was to discover whether the radios remained alive after launch. 52% survived the firing shock and continued transmitting during flight. Nearly half still failed. Yet the result changed the character of the project. The supposedly impossible step had become repeatable, often enough to improve. The next challenge was more dangerous. A radio that survived inside a shell was only an experiment. A useful fuse also had to prevent that shell from exploding beside the ship that fired it. The danger began before the projectile encountered any aircraft. A proximity fuse could react to the gun barrel. the ship, nearby rigging, or the sea. If its firing circuit became active immediately, successful detection could become catastrophic. The device therefore needed to remain harmless during loading, firing, and the first portion of flight. Only after reaching a safe distance could it become an armed radio fuse. Designers attacked this problem with more than one barrier. An auxiliary detonator helped prevent the main explosive charge from functioning inside the bore. That protection did not solve the danger of a burst just beyond the muzzle. The fuse required a delay that would isolate its firing function during the opening fraction of a second. Early experimental models used an electrical resistance and capacitance delay. A mechanical clock was also developed to provide a more dependable safety interval. The intended delay was roughly 0.3 to 0.5 of a second after firing. That interval sounds trivial on the ground. For a fast projectile, it represented hundreds of feet of separation from the gun crew. The safety system also had to survive the same launch forces as the radio. A clock that jammed could prevent detonation entirely. One that ran too quickly might arm the shell while the firing ship remained dangerously close. By the middle of 1942, a satisfactory mechanical safety clock had been developed. The major pieces of the naval fuse now existed together. There was a radio circuit capable of recognizing a nearby target. There were miniature components increasingly able to survive launch. There was a power system for the brief operating life. There was finally a practical method of delaying activation beyond the muzzle, but component tests could not reproduce an actual engagement. The Navy needed to fire complete fuses from a warship against moving targets. In August 1942, the new cruiser Cleveland became the platform for that test. Radio-controlled aircraft served as targets. They offered realistic motion without placing a pilot inside the intended fragment pattern. The 5-inch guns still relied on the ship's fire control system to direct shells toward the drones. The fuse did not guide the projectile. It could only rescue a shot that passed close enough. This distinction mattered. The new technology was not replacing the director, radar, gun crew, ammunition handlers, or gun itself. It was closing the final gap left by their combined errors. During the trial, proximity-fused shells burst around the drones as intended. The results were judged satisfactory. The test confirmed far more than the operation of a laboratory circuit. Complete projectiles had survived storage, handling, loading, firing. And flight, their safety mechanisms had delayed activation. Their radios had reacted to airborne targets. Their detonators had converted that reaction into useful bursts. Now the bottleneck moved from physics to production. In September, full-scale manufacture began at the Crosley Corporation. The decision introduced an entirely different form of risk. A skilled laboratory group could inspect every experimental unit and adjust its methods after each failure. A factory had to build large numbers with parts supplied by other factories. Workers needed repeatable procedures. Inspectors needed measurable standards. Military planners needed confidence that a fuse assembled weeks earlier would still work after shipment across an ocean. The electronics also existed in a strange category. They were precision instruments intended to be destroyed on their first use. Traditional radio manufacturing valued durability over years. This project demanded reliability for seconds after an exceptionally violent launch. A fuse that functioned perfectly on a test bench, but failed after firing, had no military value. Neither did a rugged unit whose radio response varied unpredictably. Production exposed weaknesses that small experimental batches had hidden. Components differed slightly from one supplier to another. Assembly errors could change circuit behavior. Protective materials could soften with heat. Soldered joints could crack. Batteries could deteriorate before reaching the fleet. Early production was consequently troubled. The program responded by making quality control part of the weapon design. Section T assumed responsibility not only for development, but also for monitoring production quality. Its expanding duties exceeded the facilities available at Carnegie. Johns Hopkins University became the institutional home of a new laboratory in Silver Spring, Maryland. That organization became the Applied Physics Laboratory. Its creation revealed what the small fuse was becoming. This was no longer a clever device supported by a few physicists. It was a network connecting research, naval operations, industrial engineering, procurement, inspection, and combat feedback. The Mark 32 fuse emerged from that network for the Navy's 5-inch projectile. Production models reached the fleet during November and December 1942. Their secrecy reflected another unresolved danger. If an intact fuse fell into enemy hands, its principles and construction could be examined. Operational use was therefore initially restricted to engagements over water. A failed shell would sink beyond easy recovery. The Navy had built a weapon that could make near misses lethal. Before commanders could exploit it everywhere, they also had to keep its existence from becoming an enemy advantage. Secrecy shaped where the new Fuse could fight. Over the Pacific, a defective projectile would usually disappear into deep water. Over land, a dud might remain intact enough for enemy technicians to examine. The earliest combat employment was therefore confined to situations where recovery appeared unlikely. Crews also avoided naming the mechanism openly. The letters V and T obscured the fact that the fuse reacted to proximity. In fleet communications, coded language further concealed which ammunition had destroyed an aircraft. The secrecy protected more than a circuit diagram. An intact specimen could reveal component choices. Manufacturing methods, radio behavior, and possible countermeasures. It might also tell an opponent that a near miss had acquired a new meaning. Helena's first success demonstrated that the restrictions still allowed valuable combat use. A Japanese dive bomber had approached beyond what its pilot apparently considered effective anti-aircraft range. The cruisers, after 5-inch guns fired, the second salvo brought the aircraft down. The fuse had converted the volume around the target into a lethal zone. One engagement could not prove how the weapon would behave across the fleet. Weather varied. Targets approached at different speeds, heights, and angles. Shells passed above waves, near friendly formations, and through dense anti-aircraft fire. The radio response could be affected by conditions that had not appeared during controlled trials. Combat reports therefore flowed back into the development system. Failures were not treated as a separate problem belonging only to sailors. They became engineering information. Designers adjusted sensitivity, safety intervals, batteries, and circuit behavior. Factories altered production methods. Inspectors looked for defects revealed by service rather than laboratory testing. This loop allowed the fuse to improve while it was already at war. Later models were more reliable and sensitive than the first Mark 32. Reserve batteries helped solve the storage problem. Their electrolyte remained separate until the shock and rotation of firing activated the power source. This prevented ordinary battery chemistry from slowly degrading the fuse while it waited aboard ship. The projectile S-violence thus performed a useful task. Setback broke the internal container. Spin distributed the electrolyte into the battery structure. The same launch that threatened to destroy the radio helped switch it on. The fuse still could not make an inaccurate gun accurate. If the shell passed too far from an aircraft, no detonation pattern could bridge the distance. Its effect depended on an entire defensive chain. Search radar warned the ship. Tracking and fire control equipment measured the target S movement. Directors calculated a solution. Guns trained and fired. Loaders maintained the ammunition flow. Only then could the radio fuse correct the final error. This explains why accounts that describe it as a shell finding an aircraft can mislead. The shell did not chase anything. It completed the work of a coordinated crew and several machines. The system's growing effectiveness altered the economics of anti-aircraft fire. Pre-war and early wartime estimates could require thousands of conventional rounds for each aircraft destroyed. A later applied physics laboratory assessment placed typical time-fused expenditure near 2,400 rounds per aircraft. By the war's end, proximity-fused ammunition reduced the figure to roughly 400. These were broad operational averages, not a guarantee for every engagement. Target behavior, gun control, visibility, crew quality, and attack geometry still mattered. Yet the direction of change was unmistakable. Ships needed fewer favorable coincidences to produce a damaging burst. That improvement arrived while American naval operations were moving steadily closer to Japanese-held territory. Carrier task forces were becoming larger and more persistent. Their ability to remain near hostile airfields depended on layered defense. Fighters intercepted attackers at distance. Radar extended warning. Screening vessels created additional barriers. Automatic guns defended the final approaches, the 5-inch battery. Using radar fire control and proximity ammunition expanded the deadly portion of that defensive envelope. Japanese aircrews could react. They could approach low, exploit clouds, attack from several directions, or compress the defender's warning time. Low altitude presented a genuine technical complication because an overly sensitive fuse might react to the sea. The defense therefore remained imperfect. Aircraft continued to penetrate it. Ships were still struck, damaged, and sunk. The proximity fuse did not make the fleet invulnerable. It made each approach more costly and reduced the protection offered by a narrowly missed shell. By late 1944, that distinction had become especially important. Japan increasingly used aircraft not merely to release weapons, but to become weapons themselves. A conventional attacker could turn away after dropping a bomb or torpedo. A suicide aircraft continued toward the ship until destroyed or impacted. Stopping it required damage early and severe enough to break the attack. The Fuze now faced the hardest version of its original problem. It had to turn proximity into destruction before a determined aircraft crossed the final few thousand yards. The kamikaze changed the defender's measure of success. Damaging an aircraft was no longer enough. A burning plane could remain controllable for the seconds required to reach a ship. Even a dead pilot might leave an aircraft following its final trajectory. The defensive system had to destroy control, break the airframe, or deflect the attack before impact. Japanese planners also avoided presenting one simple target pattern. Attacks could be staggered by altitude, direction, speed, and time. Some aircraft approached low enough to reduce radar warning. Others used cloud cover or arrived amid conventional raids. Several attackers could force directors and gun batteries to divide their attention. These methods attacked the network around the Fuze. A radio inside a shell could not detect an aircraft that the ship had not located. It could not decide which threat deserved priority. It could not prevent directors from becoming saturated. Nor could it guarantee that fragments would immediately disintegrate a diving aircraft. The 5-inch guns worked best before the attacker entered the crowded final defensive zone. Their proximity-fused shells created bursts without requiring direct hits. Closer in, 40mm and 20mm weapons added dense automatic fire. Combat air patrols formed the outer layer. Radar-directed fighters, picket ships, lookouts, communications teams, and gun crews all contributed to the same result. The Fuze strengthened one layer rather than replacing the others. A wartime Navy summary from April 1945 evaluated improved fire control methods and VT ammunition against suicide aircraft. It concluded that an attacker engaged inside 4,000 yards had a sharply reduced chance of surviving. When those systems worked together, the wording mattered. The advantage belonged to a combination of control and ammunition. It was not attributed to the Fuze alone. The same report expected newer VT models to improve 5-inch effectiveness further. Shorter arming distances brought the useful burst zone closer to the ship. Greater sensitivity increased the chance of reacting at the right point. These improvements answered weaknesses exposed by combat. They did not erase the human cost. During the Okinawa campaign, kamikazes sank or damaged numerous American vessels. Destroyers and radar picket ships operating on the defensive perimeter endured especially severe attacks. The fleet survived offshore. But survival was purchased by fighters, gun crews, damage control parties, and sailors aboard the ships that absorbed the blows. The proximity Fuze helped make sustained operations possible. It did not make them safe. Its contribution was strategic because the fleet could remain near the island despite land-based air attack, naval gunfire, carrier aviation, transport, and supply depended on that continued presence. A component hidden in a projectile therefore supported an operation far larger than the gun that fired it. The causal chain ran from radio reflections to fleet endurance. Yet the Pacific was only one arena where the Fuze changed the defensive equation. In 1944, Britain faced a different kind of aircraft. It had no pilot. The German V-1 flying bomb crossed the channel under pulse jet power. It followed a preset course toward southern England and carried a large explosive warhead. Its characteristic engine noise announced danger, but its speed and small size made interception difficult. The weapon did not evade deliberately. It did not turn away after releasing a bomb. Like a kamikaze aircraft, it continued until destroyed, failed mechanically, or reached the end of its programmed flight. Britain constructed a layered defense using fighters, anti-aircraft guns, balloons, radar, and observers. The system evolved rapidly as launch sites and flight paths changed. At first, guns positioned inland faced a dangerous problem. Shells that missed could fall over populated territory. Moving the gun belt toward the coast reduced that hazard and gave batteries clearer engagement zones over water. Radar-assisted fire control improved prediction. Proximity fuses addressed the final timing error. The British requirement also forced continued adaptation of the American-developed projectile design. British naval and anti-aircraft guns used different projectile dimensions and experienced different launch forces. A fuse suitable for the American 5-inch shell could not simply be inserted into every British round. The device had to be reduced in diameter and mechanically adapted without losing reliability. Some British guns imposed even greater acceleration than their American counterparts. Protective wax that supported components in cool conditions could soften in heat. Assemblies had to be fastened more rigidly. Safety mechanisms had to function under different rates of spin. The weapon's apparent simplicity disappeared again. There was no universal radio fuse. There was a family of carefully matched designs. By the summer of 1944, those designs entered a defensive contest over southern England. The target flew straight and fast. The defenders could predict its corridor. Radar could direct the guns. Now the projectile only needed to decide exactly when a predicted near miss had become close enough. Against the V-1, the entire chain finally operated at scale. The first nights of the V-1 offensive exposed weaknesses throughout Britain's defensive arrangement. During the attack beginning overnight on June 15, 1944, Germany launched 244 flying bombs. The combined defenses destroyed only 3370 reached London. Anti-aircraft guns accounted for just 11 of those early interceptions. Britain possessed roughly 1,000 guns in the defense scheme, but their location limited what they could accomplish. Many stood on the Kent Downs between the coast and London. Fighters and guns consequently operated across overlapping areas. A pilot pursuing a flying bomb could enter friendly anti-aircraft fire. Gun crews might have to stop firing while fighters attempted an interception. The land beneath the engagement zone also increased the danger from falling shells. Technology alone could not solve this geometry. Air Marshal Roderick Hill, commanding air defense of Great Britain, ordered a fundamental reorientation on July 13th. Approximately 1,000 guns and 23,000 personnel were moved from inland positions toward the coast. The new arrangement separated fighter and gun zones more clearly. Fighters could engage farther out or beyond the gun belt. Batteries gained cleaner fields of fire as the weapons crossed the shoreline. Missed shells were more likely to fall into the sea instead of populated countryside. The move also placed the V-1 inside a carefully organized corridor. Its speed remained high, but its course was comparatively predictable. Gun-laying radar measured the incoming weapon. Control equipment produced a firing solution. Batteries filled the predicted path with shells. Proximity fuses made each sufficiently close passage more dangerous. The result was not one machine defeating another. It was a redesign of the battlefield around the machines. The fuse became far more effective because the defensive system created conditions suited to it, according to the Royal Air Force Museum's assessment. The redeployment and new equipment increased gun lethality fourfold. American-built gun-laying radar and proximity-fused ammunition were central to that improvement. So were the decision to move the batteries, the separation of engagement zones, and the crews who operated the system continuously. No single contribution should absorb the credit of the others. The countermeasure ladder against the V-1 had several rungs. Fighters used speed and cannon fire to destroy the weapon. Some pilots approached closely enough to disturb its airflow and roll it out of control. Barrage balloons threatened those flying at suitable altitude. Anti-aircraft batteries covered the coastal corridor. Bombing attacks struck development facilities and launch sites. Allied ground forces eventually overran launching areas in France. Each measure removed part of the threat. None explains the outcome alone. During the wider campaign, anti-aircraft guns destroyed more than 1,800 V-1s. Fighters brought down a similar number, with recorded fighter totals near 1,771. Barrage balloons accounted for approximately 200. These totals describe a campaign extending beyond the first coastal transformation and involving changing launch methods. They should not be treated as a clean experiment comparing one weapon with another. They do show that artillery had moved from weak early performance to a major share of the defense. The proximity fuse helped accomplish that reversal because the target could no longer pass harmlessly between precisely timed bursts. A conventional time fuse asked the control system to predict both the shell's path and the exact instant of detonation. A radio fuse removed the second prediction from the ground crew. Once the shell entered the correct region, the target's own reflected signal helped determine the burst. The German weapon, therefore, supplied the final input to the device intended to destroy it. This was the system revelation hidden inside the tiny radio. The fuse did not improve the radar's knowledge. It reduced how perfectly that knowledge had to be converted into timing. It did not eliminate error. It made a certain amount of error survivable for the defender. London still suffered heavily. Thousands of flying bombs reached Britain, and civilians were killed. Injured, displaced, or forced to live beneath the repeated sound of pulse jets, the sudden silence of an engine could mean impact was only moments away. Any account centered on technical success must retain that human reality. Better defenses reduced the number arriving. They could not undo the damage already inflicted. By September, Allied armies had overrun many of the French launching sites. Germany continued attacks by other routes and from aircraft. But the original offensive against London declined. For the proximity fuse, however, the European story was about to change direction. The security rule that had confined it largely to water had preserved its secret. Now Allied armies were fighting across France and Belgium. Their artillery faced troops concealed in trenches, forests, villages, and snow-covered positions. A fuse designed to sense an aircraft could also sense the ground. If released for unrestricted land warfare, it could burst a shell above cover instead of burying it beneath the surface. The near miss was about to become an airburst. Ground combat required the same fuse to interpret a different kind of reflection. Against an aircraft, the radio response strengthened as the projectile approached a discrete object in open sky. Against terrain, the Earth itself became the target. The fuse had to trigger while the shell was still descending toward the surface. Detonation above the ground scattered fragments downward and outward. That changed which forms of cover remained dependable. An impact-fused shell could bury itself in soft soil before exploding. Much of its energy might be absorbed by the ground. A time-fused shell could create an airburst, but its height depended on accurate timing. Observers might adjust the setting after watching earlier rounds. Darkness, snow, poor visibility, and changing range made that process harder. A proximity fuse determined the final interval independently. The artillery crew still selected the target and fired the mission. The Shell-S radio completed the height-of-burst decision during descent. This made airbursts practical without demanding the same precision from observers and fuse setters. The prospect had existed since early development. It had also created the program's greatest security concern. A naval dud could sink, a field artillery dud could land behind German lines for much of the European campaign. Proximity ammunition was therefore withheld from general ground use. The Allies possessed the weapon but restricted the conditions under which it could influence battle. By late 1944, the calculation changed. Germany was already under pressure from east and west. The value of immediate battlefield use increasingly outweighed the danger of technical recovery. In December, the fuses were released for unrestricted employment in Europe. The timing coincided with Germany's offensive through the Ardennes. Storms and low cloud initially limited Allied air power. Snow, forests, broken terrain, and scattered villages shaped the ground fighting. German troops used foxholes, trenches, tree lines, and reverse slopes to reduce exposure. Those positions remained valuable. They were simply less complete against fragments arriving from above, when proximity-fused shells burst over personnel in the open or shallow cover. The Earth could no longer shield them as effectively. The familiar response to artillery had been to get below the line of lateral fragments. An airburst changed that geometry. Tree cover did not guarantee safety either. Branches could affect detonation, and explosions among trees could add splinters to the fragment field. The result was especially severe where troops were concentrated. This did not mean every shell found an ideal height. Terrain, vegetation, fuse reliability, dispersion, and firing data still influenced the pattern. Deep bunkers, substantial overhead cover, and armored vehicles offered protection that a shallow foxhole could not. Field artillery also depended on observers, communications, ammunition supply, weather data, trained crews. And functioning guns, the fuse improved the terminal effect of that system. It did not create targets or deliver shells by itself. American artillery units used the new ammunition during the Battle of the Bulge, with results strong enough to reach senior commanders quickly. On December 29, General George Patton described it in a letter to the War Department. "The new shell with the funny fuse is devastating," he added. That its wider adoption might require armies to reconsider their methods. The remark was contemporary and specific, but it should not be enlarged into a claim that the fuse won the battle. The German offensive failed for many connected reasons. American units resisted at critical road junctions. Allied commanders moved reserves against the penetration. Patton's Third Army turned north toward Bastogne. British forces helped secure the line toward the Meuse. German fuel, transport, and operational assumptions deteriorated. When weather improved, Allied aircraft returned in strength. The proximity fuse was a major addition to Allied artillery effectiveness within that larger response. Its strategic importance came from timing and scale. It arrived when German infantry needed concealment, bad weather, and broken ground to compensate for Allied advantages. Airbursts weakened the protection offered by those conditions. A countermeasure that worked against impact fire became less reliable. A trench still protected against bullets, a forest still blocked observation, snow still concealed movement, but none could be trusted in exactly the same way once shells began detonating overhead automatically. The small radio had now crossed 3 distinct battlefields. At sea, it reacted to aircraft attacking ships. Over Britain, it helped guns engage pilotless flying bombs in Europe. It turned the ground into the signal that triggered an airburst. The mechanism remained almost unchanged. The surrounding system changed completely. That adaptability explains why the Fuze importance cannot be measured by one celebrated engagement. Its larger achievement was industrial and organizational. Different services in Allied countries needed different projectile sizes, safety intervals, sensitivities, and production schedules. Millions of units had to perform after storage and shipment. Factories had to build disposable electronics at a rate laboratory craftsmanship could never support by the final year of the war. The question was no longer whether a radio could survive inside one shell. It was whether an entire industrial network could make tens of millions survive reliably enough to change warfare. Mass production did not begin after development ended. The design, factories, and combat requirements changed simultaneously. This created a problem unlike ordinary ammunition manufacture. A metal shell could often be inspected through dimensions, weight, material, and explosive filling. The VT fuse contained an electronic behavior that might fail despite appearing physically complete. Quality control therefore had to test components, assemblies, and samples under conditions resembling service. Vacuum tubes needed consistent electrical characteristics. Batteries needed long storage life, followed by immediate activation. Mechanical safeties needed predictable delays. Plastic noses, soldered connections, wax supports, and internal mountings had to tolerate temperature as well as acceleration. One weakness could disable the entire chain. Early dry batteries gradually lost energy. Reserve batteries reduced that risk by keeping electrolyte away from the active plates during storage. Firing broke an internal container. Projectile spin spread the liquid through the battery. Power appeared only when the fuse needed it. Other changes controlled excessive sensitivity. A naval fuse flying low over the sea might react to waves. Automatic control within later circuits reduced unwanted responses while preserving the ability to sense an aircraft. The Mark 58, developed for the American 3-inch 50 caliber gun, included wave suppression features. Its predecessor had not proved satisfactory in that application. This is why wartime performance cannot be assigned to one timeless device called the proximity fuse. The early Mark 32 that reached Helena was not identical to later naval or field artillery models. British guns required their own adaptations, different projectile diameters. Spin rates, launch shocks, and tactical purposes demanded different solutions. A successful principle still had to be engineered for every physical environment. The production network expanded across numerous companies and suppliers. Crosley became a major manufacturer. Radio Corporation of America and Eastman Kodak participated in British-oriented production. Other firms supplied tubes, batteries, plastics, and precision components. The Applied Physics Laboratory coordinated development and quality oversight. Military organizations determined requirements and controlled deployment. British and Canadian work contributed to the wider cooperative program. The result was Allied, even though the successful mass-produced gun projectile system emerged principally through American development and industry. More than 23 million proximity fuses were produced for American and Allied forces during the war. That number represented more than material abundance. It meant that specialized electronics had become expendable ammunition. Each functioning device existed for only a few seconds after launch. Years of research, factory labor, inspection, shipping, and tactical preparation disappeared in one explosion. Its value came from making that brief life consistent. This scale also defeated a weakness that could have ruined the concept. No electronic device of the period was perfectly reliable. If only a few exquisite fuses existed, commanders might reserve them or distrust variable results. Millions of standardized units allowed the weapon to become an operating method. Gun crews did not need a laboratory specialist beside each mount. They needed correctly marked ammunition, suitable procedures, and confidence in the supply system. The craftsmanship was embedded in production controls rather than performed at the gun. Enemy nations had explored proximity detection concepts. German researchers pursued several Fuze methods, and captured documents later showed work continuing during the war, but recognizing the principle was not equivalent to fielding a rugged radio fuse in mass-produced gun ammunition. The decisive gap lay between possibility and repeatable service use. Miniaturization alone was insufficient. Ruggedness alone was insufficient. A working prototype was insufficient. The weapon required all of them, joined to industrial scale and an existing fire control network. It also invited countermeasures and further development. An opponent who understood the operating frequency and sensitivity might attempt electronic interference. Terrain and sea reflections could confuse early models. Low-level targets could exploit arming distance. Attackers could saturate directors, approach from several bearings, or compress warning time. Armor and strong overhead cover limited ground effects. Every improvement created a new boundary rather than permanent superiority. The Fuse post-war descendants continued into anti-aircraft, artillery, mortar, rocket, and missile applications. The wartime program also left a scientific institution behind. The Applied Physics Laboratory moved from proximity fuses toward guided missile defense and other sensor systems. Engineers who had learned to make electronics, survive shock in extreme environments, carried that knowledge into later technologies. James Van Allen, who worked on rugged miniature tubes at the laboratory, later designed instruments for early American satellites. The demands were different, but the engineering inheritance was recognizable. Electronics again had to remain small, reliable, and functional in a hostile environment beyond immediate human reach. That legacy can make the wartime object seem like an inevitable step toward modern sensors. It was not inevitable in 1940. It was a weapon built through repeated failure under the pressure of aircraft attacks, flying bombs, and artillery combat. Its success depended on accepting a strange proposition. The most sophisticated part of the shell would also be the part deliberately destroyed every time it worked. The fuse did not remove uncertainty from war. It moved one decision from the gun crew into the shell. Sailors still had to detect the attacker. Radar operators still had to maintain a track. Directors still had to calculate a useful solution. Loaders and gun crews still worked while aircraft approached with bombs or with no intention of turning away. On land, observers still had to locate targets, communications had to survive, and ammunition had to reach batteries. Behind them stood workers manufacturing radios they would never see used. The results also carried a cost beyond engineering. Japanese aircrews died inside the defensive envelope. German soldiers were caught beneath airbursts that defeated shallow cover. British civilians remained exposed whenever the V-1 defense failed. American and Allied sailors died even when the layered system worked against most attackers. Technical effectiveness did not make those experiences clean. It only changed the probabilities within them. Return to Helena on January 5, 1943. A Japanese aircraft approached the cruiser. The guns produced a solution and sent 5-inch shells into its path. Inside one projectile, acceleration activated a power source. A miniature radio transmitted. The aircraft reflected the signal. The circuit recognized the narrowing distance and triggered the burst. That brief sequence was supported by years of British and American research, repeated failures, industrial inspection, naval training, and combat feedback. The shell did not strike its target. The system behind it had made a direct hit unnecessary. That was the proximity fuse's real achievement. It did not teach artillery to aim perfectly. It taught a disposable radio to recognize the final error and act before the moment was gone. If you value documentary stories about the systems hidden inside wartime machines, subscribe for the next one.